I've had several requests to do a retrosynthetic analysis for Test 2 in Organic Chemistry 2. Here's your target molecule for this example. You are supposed to outline a retrosynthetic analysis for the target molecule that ends with saturated alcohols of 5 carbons or less and or benzyl alcohol. Show the forward synthesis with appropriate reagents in the other box. This stipulation is the stipulation for your test. Your synthesis must incorporate either an acetoacetic ester synthesis or a malonic ester synthesis. The elegance of these two synthetic methods is that in both the acetoacetic ester, illustrated here, and the malonic ester, illustrated here, we have an easily accessible hydrogen that can be taken off with a simple base such as hydroxide with a full 100% yield. That gives us access to a carbanion here or here. The carbanion can act as a nucleophile, and this will react with an electrophilic carbon that has a leaving group to put on our necessary R groups. Not these R groups. The R groups illustrated here in our target and here. The secret to this retrosynthetic analysis is to recognize that your target molecule possesses one of two features. And the feature is here. This is a derivative of acetic acid. I've circled the acetic acid portion here. If you recognize you have a derivative of acetic acid, that indicates you will be using a malonic ester synthesis. And you will be putting on two groups. As illustrated here, and then after saponification, acidification, and decarboxylation, you will be left with this, and then you can form the correct ester at the end. So let's get started. The first step in the retrosynthetic analysis, regardless of whether you chose malonic ester or acetoacetic ester synthesis, is the removal of the second carbonyl functional group. I take that back. We'll get to that in a second. The last step in the malonic ester synthesis will be formation of the derivative of acetic acid that we see here, which is clearly a benzyl ester. Esters come from carboxylic acids and alcohols, as we learned in chapter 17. This being benzyl alcohol, I have circled it because we're allowed to start with benzyl alcohol. Now you can clearly see you have a disubstituted acetic acid on the alpha position. A malonic ester synthesis creates an alpha disubstituted acetic acid derivative. With this in mind, this is a result of saponification, acidification, decarboxylation of a malonic ester. This is a alpha disubstituted malonic ester. These bonds are easily made from the carbanion, illustrated next. Here's the carbanion. It will do an SN2 reaction on a primary carbon with a leaving group, creating the indicated bond from here to here. Now we must come up with where this came from and where this came from. The alkyl halide came from a primary alcohol. You'll notice this is not benzyl alcohol. In fact, it has 2 extra carbons that benzyl alcohol does not have. When I see this situation, I think of a Grignard attacking an epoxide to create this alcohol. I will illustrate that here. The combination of this Grignard here and this epoxide, followed by acidification, will yield this primary alcohol here. This is a couple steps away from benzyl alcohol. This is a couple steps away from ethanol. As you will see, the Grignard comes from an alkyl bromide, which comes from benzyl alcohol, and the epoxide comes from an alkene, which comes from ethanol. Now the task at hand is, how do I make this structure? Just as we made this bond here from a carbanion and a carbon with a leaving group, we can also make this bond here from the diethyl malonate anion and this carbon with the leaving group here. This is 1 step away from an alcohol. This is 1 step away from a diethyl malonate ester, which is easily made from a diol. Sorry to jump around a little bit. I have amended the question to allow you to use saturated alcohols or diols of 5 carbons or less. This will greatly assist us in making a diethyl malonate ester. Diethyl malonate is illustrated here. It comes from esterification of malonic acid, the 3-carbon dicarboxylic acid, and ethanol. Dicarboxylic acids are easily obtained by oxidizing diols. We are now ready for our forward synthesis. Benzyl alcohol can be converted to a Grignard in a 2-step procedure. First step, phosphorus tribromide converts the primary alcohol to an alkyl bromide. That followed by magnesium metal in diethyl ether or another ether solvent creates the Grignard reagent. Ethanol can be converted to ethylene oxide by first dehydrating the alcohol. Using sulfuric acid and heat. Epoxides can be made from alkenes using a suitable per-acid, such as magnesium monoperphthalate. The Grignard and ethylene oxide will react in a nucleophilic attack on the less substituted carbon, which does not matter here. They have the same substitution. And follow that by protonation. Using HCl, and you have your required primary alcohol for your synthesis. The primary alcohol then needs to be converted to a primary alkyl bromide using phosphorus tribromide once again. The other alcohol can be converted to an alkyl chloride. I could have selected a bromide once again, but it's always good to review other reactions. using thionyl chloride with pyridine as a proton scavenger. PYR is an acceptable short form for pyridine in organic chemistry. (1,3-propane diol can be converted to malonic acid using potassium dichromate in the presence of sulfuric acid in an aqueous environment. Sorry about that, that's symbol font there. Fischer esterification of malonic acid will give our malonic ester, which will be ready for synthesis. You need an alcohol, sulfuric acid, and heat. Diethyl malonate is easily deprotonated using a base such as sodium hydroxide. The alkyl chloride that we made earlier will then react with the anion to create the sigma bond required here. This mono-substituted malonic ester can be deprotonated the same way we deprotonated diethyl malonate using sodium hydroxide. The anion created is a nucleophile which, when reacted with this alkyl bromide, will create our indicated bond here. Saponification followed by acidification of diethyl malonate will yield disubstituted malonic acid. Saponification is accomplished using aqueous sodium hydroxide, and acidification using HCl. If the HCl is accompanied with heat, a beta dicarboxylic acid will undergo decarboxylation, giving us our disubstituted acetic acid. As you can see here, all that remains is for us to make the final ester that is in our target molecule. This will be accomplished using Fischer esterification, using benzyl alcohol in the presence of sulfuric acid and heat, thus giving us our target molecule. Congratulations. In summary, we took benzyl alcohol, reacted it with phosphorus tribromide to make benzyl bromide, which was converted to the benzyl Grignard using magnesium and diethyl ether. Acid catalyzed dehydration of the alcohol gave an alkene, which was reacted with magnesium monoperphthalate, a per acid, to create an epoxide, which when mixed with a Grignard undergoes an electrophilic addition followed by acidification to create this alcohol with 2 more carbons. Bromination, as before, creates a primary alkyl bromide, which we will use in our synthesis. This primary alkyl chloride will be used in the synthesis. It was created directly from the alcohol here. Once again, I could have used PBr3, but I chose to use SOCl2 and pyridine. Oxidation of this diol to this dicarboxylic acid, malonic acid, is followed by esterification to yield a diethylmalonate ester, which is readily deprotonated using sodium hydroxide to create a carbanion nucleophile, which will do an SN2 reaction on this primary carbon, creating this carbon-carbon bond here. This proton is easily abstracted using sodium hydroxide to give this substituted diethylmalonate anion, which will act as a nucleophile towards this carbon with a leaving group here, creating our second carbon-carbon bond. Saponification followed by acidification followed by decarboxylation yields a di-alpha substituted acetic acid, which we made into our final ester derivative using a Fischer esterification using benzyl alcohol and sulfuric acid in the presence of heat. And that gives us our required target molecule illustrated here.